So this is an interesting bit of kit. It's an old Suzuki ignition tester, and we have we've got a voltmeter there. Looks like it has a bunch of scales on it. You can choose to measure, looks like a bit of current or voltage, DC or AC volts. Couple of tabs for calibration and a spark gap. I presume that would be adjustable, but no, it may not be adjustable. But little spark gap down under there, and you can choose what type of test you are wanting to do. So it doesn't work. So let's start with the basics. It is a mains operated piece of kit. No batteries here. Right, so we've got our power cord, and we will see if there is any connection, any resistance through the mains lead, just to see if that is looking alright. Keeping your fingers off it because you don't want to measure your skin resistance. And we have nothing there, so we'll turn it on. And we still have nothing. We'd expect to see some resistance. I'm picking there'll be a transformer in there of some sort. So let's check the fuse, which is conveniently housed there. Got one fuse, and we have 0, so we have a good fuse. So what if we go from neutral? So in this country, neutral is on the right, so we've got phase and neutral. If we go neutral to, what about down in the bottom of the fuse socket? I don't know which one's in and which one's out. Got nothing happening there. What if we go to the metal, the thread? We got anything there? No. Or there. Okay, so we're at the top of the thread that looks like a main connection point, and we're at a couple of meg ohms. So yeah, something not connecting through right. It could be a bad power switch, or it could be in the wiring. It could be anywhere. Let's take it apart. Looks like 4 screws, and it should flip over. A little bit of weight to it. A whole bunch of cables in front. Actually, I might just empty this section out, make it easy to deal with. We're not fighting over them when we try and put it back in, because the chassis comes down to the bottom there. And it's all one unit by the look of it, so we can get rid of the briefcase. Flip it over and see what we're dealing with. Ah, look at that. When was this made? The 50s or something? Well, right off the bat I can see that there's a wire here that is melted. That one there is melted out. It's hanging, a strand's hanging out here. So it's actually clearly seen an overcurrent situation, and you can see that hanging out there. It's come out of the insulation, that black one that runs down here. So that's the sense wire off of our current shunt, of all things. This looks like our current shunt, solid bit of metal with larger wires and smaller wires for showing the reading. Also further down in here there's what looks like a fuse with wire wrapped around it, and I don't know if that was a factory intentional way of calibrating or if someone's just gone and done that to fix the fuse. So it's not too good, but we need to find out why it doesn't power on, I suppose, where our mains input reading seems to be quite high. Looking here, we've got our mains cable coming in. It comes down to the power switch, and then it goes off to... Oh, that's why we didn't get a reading on the transformer. Okay, so it goes through the power switch, and... no, I could be wrong. No, I might be overthinking this. Oh, that's the primary winding taps, of course. This fuse holder can it can be pulled off and rotated and plugged back in to choose a different voltage tap. So it's yeah, there we go. So that's what all these other color wires are for. So our primary off to the transformer, but our other side of the primary winding is through the fuse into one of the voltage taps. So we will trace that through. So we come through from our voltage selector, and our transformer is over here, and we have 100, 117, 240 and sorry, 220 and 240. So yeah, it could be either 220 or 240. Probably is set to see what it says it's set to. Set to 240 at the moment. I'll just pop that off there. A quick look at the selector. Yep. So it is currently set at 240, and that's our yellow wire. So we can do a resistance measurement on the straight across the primary and bypass the fuse there and see what's going on. So down the bottom we have our phase comes directly into there, and then we switch our neutral to the other one. So if we check our resistance there on the primary, we have 17 ohms. So that's good, that's intact, it hasn't burnt out, so that's probably fine. 15 ohms on the lower one, 220. What do we got there? 5 ohms on the 117 and 4 ohms on the 100. So that's all good. Looks like we may have an issue with our selector there, because we could not measure through the plug. So actually, while we're here, let's go from our fuse to, it should be fused to yellow, and it's not, because it's set to 240. So we have a problem with our socket then. I wonder if we adjust it to a different value and see if it switches to that. That would be interesting. Yeah, our yellow does make it all the way over. Would probably help if I put the fuse back in before I do a little test like that, eh? I don't know. Try that again. There we go. So we've got a good connection through there. Let's grab the end of our mains cable. If if we go from phase, and we know phase goes through the switch, and we have no phase to the switch. And if we go to neutral, we know that comes into the fuse, and we have nothing coming into the fuse. Okay, sorry, I had that backwards again. Neutral comes into the switch. Here we go. So we have neutral coming into the switch, which is not good because you should be switching phase. Otherwise everything's live when it's turned off, potentially. And then our phase comes into the fuse, which it does not. I think we have a broken mains cable. Certainly one thing I noticed is that ripple effect you can see there on the cable. It's quite possible that the cable is damaged right there, because it should have more of a smooth texture to it like that. So that's almost a dead giveaway that that's where our problem probably is. And we have a lot of cable to work with, so I think what I'm going to do is cut it back here where it's good, test it, and then we can feed it back through the hole there and reattach it if it's all good. Maybe it's okay at the plug. So let's check the rest of this cable. We may need to cut it back a bit further, I don't know, but that's looking highly suspect, so we'll trim it there. And of course, make sure this is not plugged in, in case you have been testing it live. Now what we want to see is whether or not we have a connection through to this end, and we will check that one there. So we have our neutral, and then if we check phase, and we have our phase. So we have a break in that horrible little piece of cable there. Alright, feed our cable through the hole there, and we want it to have a similar amount of length after the knot. So there's our old one on the right. So we will tie a knot and work it to a similar length. And what we got? Something like that. Close enough. Now we got to split the end, so just shear it apart with your fingernails. There we go. And we'll need to plenty of length there to reach the switch and the fuse, and strip a bit off. Give it a good twist, and then we'll tin the ends of it. Now we need to work out which one is phase and which one is neutral. So we're checking for phase, not that one, so it should be that one. We'll just have a bad connection. No? Meter works. There we go. There's phase. Do we have a bad connection somewhere else as well? Let me just grab a fly lead, clip it on there and there, So it's always on, and we'll give the plug a bit of a wiggle. Make sure that that's okay. I think I just had a bad connection to the terminal, but that seems all right. Cool. So that's our phase. Remembering that they put phase to the, oh sorry, that's our neutral. So that's our neutral. Remembering that they put neutral to the switch in this particular setup. Maybe there's a valid reason for it, the way that the whole thing is designed. So I'm not going to change that. It's been working like that its entire life. Get some heat into the switch and then add the wire. I always like to load the tip up with solder so that it can make sure there's enough there to form a good connection. There we go. Takes a lot of heat. That one's good, and that one is good. Alright, something's having me on here. We clearly tested connection through to each lead after I cut the other end off, but here's our neutral, right, and here is our phase. Nothing again. It might be just easier to replace the entire bit of wire, I think. So I found a cable. Never throw out cables, you never know when you'll need them. Even if they're complete, you could always cut a plug off the end and use it like this, directly in. So this should be good. Let's prove it. We go from phase. We should be getting a signal on brown. Here we go. And neutral to blue. Excellent. Alright, we've got a new knot formed. We'll get the length of our wire sorted, and we could probably cut that one off there. It's not going to matter too much, to be honest. And that one can stay that length. Make sure that there's not going to be any stress on that. So the knot's hard against the chassis. Make sure that that's the case. If it was further forward and then you put that on, it might want to pull against that because the knot's not seated yet. So this time, do we have a connection through to phase? Yes, we do. 0 ohms there. And we go to neutral. The plugs pins are a little bit dirty. It hasn't been used for a while. And we go to neutral. And we have same again. There. Again, the plug pins are dirty, but that is fine. I will give that a bit of a clean up. We need to now look at this melted wire that comes up here to this post and heads on down here. So here's the remains of it, this black one here. And it's all bundled up and tied together with the rest of the loom. So we're going to need to split that. Possibly, or maybe I just leave it in the loom and I'll run a new wire. Might be easier instead of cutting all the bundling off and risking it going everywhere. but it has got hot enough obviously to melt to things, so we need to give it a good visual and make sure that didn't melt through and melt into other wires there. We can see that when it comes down it follows this loom here and it comes around and along here, so this black one on top, it's all nice and crusty. There it goes. And it comes around into underneath here somewhere. So we may need to get that switch out to see where it attaches to. I've switched this to the off position so the line is straight down. That gives us access to 2 screws on this end. Now this knob is not keyed, so if you take it off without identifying where you started, in this case we're starting in the off position, you will then have to try and figure out where to put it back on. So we can see that it comes around the main loom and up around to this connection here. We can get that out and have a good look around and make sure it didn't go down to the bottom, which there is another black wire down there, but it's not the one we're after, it looks like. So it appears to just meet up with ground. What looks like it could be the ground for the whole system, and that's where we will reattach it to. So here is the wire protruding from the sheath it's melted out from. Separate that from the other two. So let's try and follow it back through the loom. There's some crusty greens in there going on. And hopefully make sure that it hasn't shorted against any of the other wires down in there. So I'm just following this back. I'm pulling it out as I go from its melted insulation. I think what I'll do is I'll cut it down here, and that'll allow it to be easier to pull through the bunch of wires. No, it's so bad it doesn't want to pull through. Alright, we will keep inspecting. It doesn't appear to have melted into any of the other wires, it's just melted itself. It's quite tight through that little section there, but here it comes. Here we go. Right, I will finish cleaning that up and we'll run a new wire. As there's no real need to run the wire all the way around the full length of the loom, I'm just going to go from here straight down to the switch. Get rid of the old piece. And there we have it. Now I'm wondering if how this happened was we've got our leads come in from the outside here, and these two black and red ones there, and they go through our current shunt, and they're attached to a couple of alligator clips. And yeah, I can only think maybe if you only hook up the positive lead and it found its own ground to path and it found its own path to ground through the skinnier lead because the main lead wasn't hooked up. Perhaps in that case it would have had another lead connected somewhere though. Anyway, things to note. always connect the leads exactly as needed. I'm going to leave our little fuse down in here as it is. It's hard to say if someone's done that or not. They must have. It's been in there for a while, but it's 300 milliamp anyway, so as long as that's not exceeded. Well, that's about all I can see that was wrong with this, so let's plug it in and cross our fingers and see what happens. Turn the bench lights off because I'd imagine we want to see the pilot light up. So let's do that. Oh, jeepers. You hear that humming? That's quite a noisy transformer there. A bit worried about that. May need to check the output voltages, just sort of see what's going on, but that's humming. I wonder how much current that's drawing. Turn it on. So the one making all the noise is this little guy. You can even feel it vibrating. It's not the big one. What's it feeding? There's some large resistors it's feeding into. I wonder if that diode across it is alright. Might be normal. So if I get in there and measure its output, we'll see how much is coming off it. Nothing. 0.1, no, nothing. Well, that's no good. What about to the center tap? No, nothing. Interesting. I just measured it at 1 volt AC on the primary. I don't know. Is that what it's supposed to be? Where does that come from? So I'm just going to ignore that for now, because what I thought was the primary winding goes to this light, and what I thought was the secondary winding goes to this output connector. So I'm not sure what's buzzing and why, but let's move on. We'll say it's normal, and we will focus on those two caps there. So we get our main secondary voltage from the big transformer comes in through here. There's a bridge rectifier, so stuff going on there. Let's just see if we have a voltage on there. And I can tell you that it is 8 volts on that one. And the one underneath is 0.9. It's not much, is it? Say 1 volt. So I don't know. Maybe that's normal, maybe there's something else going on. On this back panel, all of the points where the wires come in are numbered, and a lot of these wires come from the secondary taps of the main transformer, so we can check those, make sure we have the expected voltages there. Luckily, like all good bits of kit back in the day, the user manual comes with a schematic. I guess they expect you to fix your own stuff back then. Now, this is the board on the back panel. These numbers appear on the board, so we can directly see where they connect to. And on this page, we have the same board with the numbers repeated, but just showing where they, or what comes into them and what comes out of them. So we can see that we should have, so we've got a 200 volt AC winding, 100 volt AC winding, 2 volt, 20 volt and 15 volt. So we need to make sure that they're present and correct. the 200 volt line is passed through a switch which goes to, I believe that's for ignition testing, I think. What's those switches? Yeah, this switch here for PEI, ignition coil and timing light, I believe is that switch. There's a dotted line through to here. So this must be the output of the switch, and this must be perhaps the input of the switch for each position. Anywho, so our 100 volts can be switched through to either of those. And up the top row of numbers there, I believe this is our other main selector switch, because it's got our DC, AC, ohms, ranges, and then a couple other bits. This is our meter, and yeah, it's very basic. So let's focus on that, make sure we have our secondary winding voltages and see where they go into here and see what's going on there. Don't you just love thermal cameras? I thought I'd just see what may be causing the humming noise. It's probably dumping into a short somewhere perhaps. And I don't have a decent circuit diagram, but anyway, we'll switch it on and see what happens. So just for reference, here's the two capacitors that we measured the voltage on. So this is the panel on the back, and we'll switch it on. She's humming away, and right away we have items getting hot. And they are, if I point to, got a capacitor there, big resistor there, I think it's those. So that's getting up to 90 degrees. We don't want to cook them, do we? Quite possibly as Zener diodes that are shorted. Little glass diodes there. This is kind of cool. If I turn off the infrared camera and just have the video camera, it still shows the temperature spot. So you can actually get a better look at you know, what you're looking at. So we're looking around here. There's a resistor there and a couple of diodes beside it to the left. It's quite dark image, I know, but anyway, if I turn it on, we'll see that temperature spot move. There you go. So it points exactly to it. So it's a bit easier to see than just the infrared image. Now we can see that pin number 8, which goes to, so here's the diodes that are getting hot. That's the capacitor there, there's a couple of diodes. That's R4, the resistor beside the diodes. Now these, I'm guessing there's got to be a Zener, one or both are Zeners, but these are the ones that are getting hot. Comes in pin 8, and pin 8 is our 20 volt AC in. So let's have a look and see if we have our 20 volts or if it's being pulled down by some kind of fault condition which is causing all that heat. So pin 8 is there, and this pin down here is our 0 or ground winding. So here we go, 21 volts, so it's clearly capable of supplying what's required. Pin 1 should be 15 volts, so let's see if we can find one. That one there, 1 volt higher, and pin 17 should be 2 volts. 2 volts. So after doing some measurements and playing around, it appears I've numbered the switch in reverse. So I would have thought position 1 would have been all the way to the left, but it turns out that's position 3. So yeah, there's always going to be some editing error, isn't there? But it's a bit of a big one if you ask me. But I'm not going to rewire everything to suit this, because obviously it's been working all these years. So let's continue. So we've proven all of our secondary voltages are present. It's interesting why it still hums loudly. See if you can hear that. It might be normal. I don't know. I might be just chasing a red herring. Who knows? But the meter doesn't function. Let's have a look at the output of this PCB on the back. So when we've got our 200 volts coming into pin 20, it gets rectified and goes out on 18 and 19, and they go to our connector on the front panel for whatever adapter. You can plug in multiple different looms for different actions. So I guess we could make sure that we have our secondary voltage there. Pin 14 should be our rectified output. Possibly, oh no, there's a triac. So we've got a triac which seems to be switched by pin 17. Pin 17 is our 2 volt AC, so I guess it's 50 Hertz. It must be being triggered at 50 Hertz to go out to pin 14, which goes to pin 8 on the front panel connector, which is used by coil. Yes, so that is switching our ignition coil. If we have a coil plugged in here for testing, just to fire a coil, that gets through a diode there. There's another diode there which could be a Zener, I'm not sure, but there's a capacitor in series with the output, so there's that. The triac is actually switching across that, and it's ground, so it's pulling the input to ground on a regular basis. On a 50 Hertz basis, it's so it's chopping up the 200 volts coming in, isn't it? And there's our storage capacitor for that. Is it? Maybe? Not if there's a series capacitor. I don't know what's going on there. Anyway, we will check pin 14, see if we've got a pulsed output on there perhaps. So if we check, we have, there's our 220 volts on AC going in, and our DC will check across the cap, and we have 296 rectified DC. So I don't think that's loading us up. Now we'll drop our AC to our pin 16 there, and then that will be looking at our pin 14 for output. So we'll turn the knob, get our AC out here, and there's our 220 out there, and then pin 14, which is going to be coming off of the, is, I believe, that one. That's after the capacitor, so we'll go before the capacitor, and we have 140 AC after the triac. So that's 220 going in and 140 coming out. And that would make sense if it's being modulated at 50 Hertz. It's like 50%, isn't it? So here we go. Now pin 1 should be our 15 volts AC in, which is there. And we have that, it's slightly higher. And then pin 3 should be our rectified out, or regulated out. It's coming out at 3 volts. Wonder what we should expect. Now there is a Zener on this output. I'm not sure what the rating is yet, but let's remove this wire and see if it stays at 3 volts or if perhaps this is loading us down, because this actually goes out to our ohm meter, and I'm not sure if it's on a variable, or goes through a variable resistor to ground, but whether that's used for supplying the ohm meter, I'm not 100% sure. So if we take that off, and fire it up again, and we'll just see if we still have 3 volts on there. Okay, so that's jumped up to 12 volts. So that's interesting. Still humming a lot though. Okay, so the reason it drops is it's actually going through a 3.3 k ohm resistor, and then that goes to the calibration pot for the ohms range. So that's absolutely fine, and we will move on. I don't know why I didn't do this before. So I've had a closer listen around, and the humming is actually coming off these big power resistors. I think mostly this one in the back. Yeah, this one over here seems to be the one that's making all the noise. So let's have a look at where the wires go to for that one. But I'm still not convinced the other Zeners up there should be getting that hot, as we saw on the thermal camera, so there might be two things still. Having a measure, the big one has got 110 AC. The one that I think's making all the noise, 220 AC. And then the little one up there has got 16 AC on it. Okay, that's our series pass resistor there, and one that's not showing on the 15 volt rail. Nothing wrong with this system. You know, this is what happens when you try and outsmart yourself. Using the thermal camera, showing up obviously an incredibly hot Zener diode. So I can't imagine that's right. And then with the humming away, we thought it was a bad loading. And we've proven it's not that. But the meter doesn't work either, so I was kind of thinking, well, you know, what's going on there? We just need to have a closer look at that part of it there then. Where we've got pin 8, this is our hotline, and where it comes out there, on pin 9 or 12, 9, 10 and 12, they head off here and off to the, well, it looks like it's off to the meter section, but yeah, that's kind of what threw me with the meter not working. I don't know. I think it's a whole lot more simple than I'm making it. Right, so let's work a little quickly. We don't want to cook the poor little diodes, but once again we'll check the AC in on that circuit. So that's 22 volts AC on our 20 volt line. On the other side of the resistor that it goes through, we have 13 volts AC, so we've dropped 7 volts across that resistor, which is 120 ohms. Referring to our schematic again, so we've just checked R4, we've got our 20 volts in, we've got 13 at that point after the resistor. Now if we have a look, we have a capacitor that's AC coupling through to pin 10, and then we've got pin 12 and 11 and 13 doing something. And if we have a look over here, we've got pin 11 and 10. So this is a switch on the top which you push to do your calibration or test. So you push that and it gives a test. I guess the needle moves and it just makes sure things are working. It's a test switch in the normally closed position. Pin 11 and 10 are connected together. Now that being the case, we've got pin 10, which is our AC coming through here again, connected to 11, so that's going to come back up here and be rectified by this diode across this capacitor. So let's see what's going on there. And in theory, our 11 and 10 should be connected through that switch. So pin 10 and 11 should be connected, and they are. So if we check the voltage that's happening there, our AC voltage coming through to pin 11 via the switch, and we have nothing. So let's disconnect pin 10, which is going out to the switch. We should have our AC on there. So we now have our 13 volts back. And when we connect it through to here, we have nothing. Now that's going through a diode into that cap. So why do we have nothing there? Let's get our resistance range. Now that cap sits there, across here and here, and if we check our resistance across that cap, we're sitting at a dead short, and that's why we have nothing. We have that rectifier diode goes from pin 11 to 12, so we can check pin 11 to pin 12. Now that's good, 0.6 ohms there. So the only other thing it could be is that capacitor is shorted. Let's remove it and find out. Alright, we've got our little capacitor here. Is it shorted? No, it's not shorted. So is there still a short on the board? No, no short on the board. But what was there before? This wire that connects to pin 12. We have a short on this wire, so that's heading back into the system. We'll need to go look at that now. Right, so if we follow pin 12, goes it comes up here and along to what appears to be pin 1. It's kind of rubbed off, but it's got to be pin 1 of the main selection switch. So I don't know that the diagram stops at that, so we're going to have to try and figure this out, where it goes when the switch is rotated. I guess where that wire, that ground wire, melted into the loom, it may have melted into another wire, but it all looked pretty good. So let's rotate the switch and see if it stops showing as a short, because I can't imagine that's really an ideal thing to happen. I wonder if that other input diode's getting really hot now. I've removed the short off this end. Here we go. So hang on, we're starting at Okay, just check the position that I'm starting at. Oh. Okay, so in that position, which happens to be the test switch calibration position, for some reason it drops it to ground. And if I was to push that switch, it would then pass, yeah, it would end up joining pin 11 to pin 9. So once you push the switch, it's going to join pin 11 to pin 9, which says B, and on, yeah, where does B go? Right, what I'm going to do, I'll show you what I've found. I'll measure the resistance across the back of the meter, just out of curiosity, and if we have a look, and I pop my leads across the back of the meter, we get basically 0 ohms. I'm not sure what the coil of a meter like this should be. I'd imagine it'd be quite low anyway. Then if we have a look at the meter itself, down here it says full scale is 500 microamps at 100 millivolts. So yeah, I thought what I'll do is I'll just tap my bench supply on a low voltage on the back of it and see if I can make it move, see if it is going to move. Make sure that's not part of a problem with trying to get a reading on this thing. So it's currently set at 1 volt. Okay, let's set it at 300 millivolts. I've set it at 300 millivolts, and if I tap on there, then you can see it barely moves, and it's pulling 200 milliamps. So I mean, that should have swung to full scale. Now, if I up the voltage, say to 1 volt, that's 1 amp at 1 volt. It's not moving. So there's definitely a problem with the meter. It's possible that maybe when that whatever happened with that fault current that melted the ground wire, maybe it's actually backfed through the meter and burnt the coil on it. So I think we're probably at a loss to fix the meter side of it. Alright, let's check our outputs on this connector here. So I've got my diagram, and with it, instead of probing it from the back, we'll probe it this way and just make sure that we are looking at the right pins. So it's 1, 2, 3 down the right, and then it steps over 4, 5, 6, and so on. Now in the position 1, according to the diagram, we should have our output on 9 and 10 of a couple hundred volts, and we've only got 2 volts. So this is what got confusing. So let's switch it. Okay, so there's our 300 volts that we expect, but that's not in the PEI position, that's in the timing light position. So honestly, I don't know. Let's have a look at the timing light and see what pins it uses. So here's our little timing light, and the connector there, and that must go to wherever the pickup. There's our pins. Now that is actually pins 9 and 10, so if we put it that way. So in the timing light position, with the timing light, we have a couple hundred volts across those wires. And according to the diagram, the timing light should go to pin 6, which is our bottom pin here in the middle. So I wonder what uses pin 6. And if we have a look at the timing light diagram, it definitely says 9 and 10. There's a blow up of the pin configuration there, so it definitely uses 9 and 10 on the connector. Do I plug it in? Do I see if it works? Do I, you know, take a chance. Whereas in the other position, PEI, if it was labeled you know, 1, 2, 3, not 1, 2, 3. PEI is going to be one of these two here, which that's using pin 6. I mean, it must have always worked like that. And a couple hundred volts, I suppose you probably need a couple hundred volts to light the strobe, yeah? So it's probably accurate. Well, after all that, it's back in its case, and what was the end result? Just a new power cord, really, wasn't it? After trying to fault find initially the buzzing noise made me think there was an overload, but there wasn't, and then I get thrown off by the thermal camera, so don't ever trust what you're looking at on one of those. Obviously Zener diodes just run kind of warm. Yeah, there doesn't seem to be any issue other than the meter itself is fried. And that's why we weren't getting any movement on it, I would say. Because yeah, if it's only pushing at most 100 millivolts to the dial to make it move, it's never gonna flick under normal measurement conditions. So at least we got the thing turning on again, and it can be used for ignition coil testing predominantly. So thanks for watching, and yeah, not much to learn from that, I suppose, but what a way to kill some time though, huh?